Hello, my name is McGuire Radosevich. I'm a senior mathematics major at Truman State University, and today I'm going to be discussing the conjugation isomorphism theorem, going through the proof and some applications. So a brief overview for what we're going to talk about. First, we're going to review some key concepts relating to algebraic extensions and simple extension fields that are key to the development of this theory. Define some relevant terms that are particular to this theorem, state and prove the theorem, and then discuss some of the theoretical consequences of the result. First, we're going to review extension fields and algebraic elements. Well, let's say that we have two fields, E and F, where F is a subfield of E. We refer to E then subsequently as an extension field of F. Now, let's take an element of E. And let's say that that element, which we'll call alpha, is the zero of some non-zero, non-trivial polynomial with coefficients from f. If that is the case, then we say that alpha is algebraic over f. Examples to make this concrete, and also to stress the importance of precision in language, saying that something is algebraic over f, as opposed to just saying that it's algebraic, because it matters what field you're referring to. In this case, it can be demonstrated that the number pi is not algebraic over the field of rational numbers. So no matter how high the degree of the polynomial, or no matter what rational coefficients we use, we can never have it such that pi is a zero of a polynomial with rational coefficients. This is why we call pi a transcendental number, as opposed to an algebraic number. However, trivially, pi is algebraic over the real numbers because it's a zero of this polynomial right here, x minus pi. Clearly, if we substitute pi in here, and this is a polynomial with coefficients that are all real numbers, then we're going to get zero, and this is a non-trivial polynomial. So it matters what field we're talking about. Now let's say that we have the case that we have this algebraic element. We have an alpha that is algebraic over a field f. Then there is a unique, irreducible monic polynomial with coefficients from f, of which alpha is a zero. We call then this polynomial p of x the irreducible polynomial for alpha over f, and we denote it in this way. Going back, there is a unique irreducible. So irreducible means that this polynomial cannot be split up into two factors that are polynomials of degree strictly less than the irreducible polynomial. Monic polynomial means that the leading coefficient on the highest degree term is 1, or whatever the multiplicative identity is in the field that we're looking at. And then it is the case that alpha is a zero of this polynomial. That's a little abstract. Oh, let's give some examples. The irreducible polynomial for the square root of 2 over the real numbers is this polynomial right here, x minus the square root of 2. This is a degree 1 polynomial, and all of the coefficients, 1 and negative root 2, are real numbers. Irreducible polynomial for the square root of 2 over the rational numbers is x squared minus 2. Again, we have a monic polynomial here because we could multiply by factors of f, 2x squared minus 4, square root of 2 would also be a zero of that. But since we want uniqueness, we stress that this has to be a monic polynomial. This is unique in that it is monic and it is irreducible over the rational numbers, and the square root of 2 is a zero of it. So the square root of 2 is of degree 2 over the rational numbers, and degree 1 over the real numbers. One specific type of algebraic extension fields are simple extensions. So say that we have an extension field E of f and an element of E that is algebraic over f. I'm going to consider the evaluation homomorphism phi sub alpha, which is the evaluation homomorphism that acts on polynomials with coefficients from f with respect to alpha, and it maps into that extension field E, since alpha is in E, and E is a field. And we define it in the way that the evaluation homomorphism is always defined. So we have a polynomial, And for any coefficient, which is an element of f, we leave it fixed. And anytime we have x, we replace it with alpha, because we're evaluating a polynomial at alpha. When we have that, we can check that the image of that evaluation homomorphism with an algebraic element is a field. And we denote this field f adjoined alpha. Looks like f of alpha, we call it f adjoined alpha. Again, that's the image of the evaluation homomorphism at alpha on this integral domain of polynomials with coefficients from f. It's a subfield of E, which is the extension field of f of which alpha is an element. That's one way to think about f adjoint alpha, but what I think is an easier way to think about f adjoint alpha is that it is the smallest field that contains both f and the element alpha. So what that means is, if you think about how fields are constructed, it's going to include everything in f, and then it's going to include all of those products of alpha and powers of alpha with all of those elements of f, so we can make sure that we have closure in the field. An example of this would be, we could take the square root of 2 and we could adjoin it to the field of rational numbers. This field contains all of q, and it also contains everything that can be expressed as a rational number times the square root of 2. Whether that's 3 root 2 or 1/2 root 2, or root 2 over 2, then that is how we construct that particular field. Now, this field q adjoining the square root of 2 also has to include all of the powers of the square root of 2. However, since the square root of 2 squared is 2, which is a rational number, we already have closure after we've included just degree 1 terms of the square root of 2. We're going to move on to conjugates, which are particular to the conjugation isomorphism theorem, as the name would suggest. In this case, we're going to have two algebraic elements from E, an extension field of F, that are algebraic over F. We say that these two elements are conjugate over F if the irreducible polynomial of alpha over F equals the irreducible polynomial of beta over F. So alpha and beta are conjugates if and only if they are the zero of the same unique irreducible harmonic polynomial over F. An example of this that all of us are familiar with, even since high school algebra, would be if we take complex numbers, numbers that have an imaginary component. We take I and negative I, the additive inverse of I, which is the square root of -1, we can check pretty easily that these two numbers are conjugate over the field of rational numbers. Each is a zero of this polynomial, p of x equals x squared plus 1. Square root of -1 squared is -1, -1 plus 1 is 0. And this is true in general for any complex number, a plus bi. We have a number a plus bi, where a and b are real numbers, then a minus bi, as we learned again in high school algebra, is going to be a conjugate. I think it's pretty interesting that we called them conjugates back then and didn't really know why, and unless your high school algebra teacher took some pretty advanced abstract algebra, then even he or she might not have known why, but everything has a reason. And we're going to show that these simple extension fields formed by conjugates are isomorphic to one another. So for instance, if we took the rational numbers adjoin I, and we took the rational numbers adjoin -I, then we would get two fields that are isomorphic. That's why we call them conjugates, because we can map them onto each other, and that's going to become more clear when we state the general isomorphism that can be applied to any case. This result of showing that these simple extension fields between conjugates is isomorphic is fundamental to developing algebraic theory, because what it does is it gives us a way to relate algebraic extension fields to groups of permutations of those fields. Because in its simplest terms, if we have multiple elements that we're adjoining to this field, then every isomorphism under this theorem is going to be a permutation of those zeros of the conjugates. And so that gives us a way that we can relate group theory, which we learned with permutations, to field theory with these extension fields that we've been working with for a little while now. And that's key to developing some pretty profound results that we'll discuss later. Now here is the statement of the conjugation isomorphism theorem in its simplest terms. We have F that is a field, and we have alpha and beta that are two algebraic elements over F. We say that the irreducible polynomial of alpha over F is a degree n polynomial. And this function, psi sub alpha beta, which maps F adjoint alpha into F adjoint beta, defined in this way, I'll come right back to it and explain it, is an isomorphism if and only if alpha and beta are conjugate over F. What we're saying is that F adjoint alpha and F adjoint beta are isomorphic if and only if alpha and beta are conjugates under this map, isomorphic under this map. So what is this map? What does it do? Well, at first glance, it looks a little complicated, but really it's not. The only thing that this does is it takes a general element of F adjoint alpha, which is expressed in this manner as powers of alpha multiplied by elements of F. We leave everything in F fixed. So A sub 0, which is the only thing that's not multiplied by a power of alpha, is left fixed, as are each of the coefficients of these powers of alpha when we move over into this other field. The only thing that's changing is with the alpha and the beta. We replace alpha with beta. So A1 alpha becomes A1 beta. A2 alpha squared becomes A2 beta squared. So what it does is it leaves everything in F fixed and maps alpha onto beta. It's the easiest way to describe this isomorphism. Well, it's an isomorphism, as we'll demonstrate with the proof, if and only if these two elements are conjugate over F. The forward direction proof is pretty straightforward. In the forward direction, we assume that this map that we described is an isomorphism with all the properties associated therewith. Our goal is to show that the irreducible polynomials of these two elements are the same, show that they're conjugates. By our hypothesis, we have that the irreducible polynomial of alpha over F is a degree n polynomial. We can express it in general terms as follows. We can take elements of F and multiply them by powers of x until we get x to the n. X to the n is going to have a coefficient of 1 because this unique polynomial is a monic polynomial, as we established earlier, but everything else is going to be multiplied by an element of F, which we index from 0 to n minus 1. And since we have assumed in this direction that this is an isomorphism, one of the fundamental properties of isomorphisms is that isomorphisms map 0 onto 0. So if we're going from one field to another, an isomorphism maps the 0 from the first field onto the 0 from in the image field. So what we can do is we can take this irreducible polynomial of alpha over F, and we can substitute alpha in for it and determine the image of that element of F adjoint alpha under this function psi. And we can write it in two different ways. So in one sense, we write psi as we expressed it in the statement of the theorem, where we leave everything in F fixed and we map alpha onto beta. So the image of this element is, in one sense, this element right here of F adjoint beta. However, in another sense, we know that this is really equal to whatever the 0 is in F, because alpha is by definition the 0 of this polynomial. And since the isomorphism maps 0 onto 0, then in another sense, we're mapping the 0 from F onto the 0 from F. So on the right-hand side, with our last two equalities here, we have 0 equals this element right here, which if we replace beta with x, we find that beta is a 0 of this polynomial, which we've already demonstrated is irreducible and monic. So beta is a 0 of the same irreducible polynomial. So we conclude that alpha and beta are conjugates. The other direction is a little more subtle, a little more clever. In this direction, we assume that the irreducible polynomials are the same, namely that alpha and beta are conjugates. And since alpha and beta are algebraic, we know that this polynomial p of x exists, and it has rational coefficients from f. What we're going to do is we're going to examine that relationship between the evaluation homomorphism and that field f adjoint alpha that we discussed early on when we were talking about simple extensions. The evaluation homomorphism acted upon this integral domain, the field of the domain of polynomials with coefficients from f. Whether we have alpha or beta, those evaluation homomorphisms are going to have the same kernel because each of these has the same irreducible polynomial. And the kernel of that evaluation homomorphism is, as we learned earlier, the principal ideal generated by that irreducible polynomial. The general theme of abstract algebra, and it applies here as well, is that if we construct a factor ring where we mod out by the kernel, then we get something that's isomorphic to the image. So we have two natural isomorphisms here. We denote psi sub alpha and psi sub beta. Each of these has the same domain, but the difference is the range, f adjoint alpha and f adjoint beta. These are natural, and we'll see why when we use this fact later in the proof, but what we're going to be doing in these isomorphisms is we take representatives of cosets from here, and their image under this natural isomorphism is whatever the image of the evaluation homomorphism of those representatives would be in the field f adjoint alpha. Same thing with f adjoint beta, except we're substituting beta in for the representatives of these cosets. Now, just by this statement right here, we have already shown that f adjoint alpha and f adjoint beta are isomorphic to each other, because isomorphism is an equivalence relation. So we've shown that f adjoint alpha is isomorphic to this factor ring here. F adjoint beta is isomorphic to the same field. And so by transitivity, f adjoint alpha is isomorphic to f adjoint beta. The only thing that is left to show is that it's the isomorphism that we want. That if we compose psi sub beta with the inverse of psi sub alpha, then we get the isomorphism that leaves f fixed and maps alpha onto beta. That's the last step, and we'll show it right here. What we're going to do is we're going to pick an arbitrary element of f adjoint alpha. We can express it in this way, as we showed earlier. And we're going to find the image of that isomorphism that we constructed and see if it's what we want. Now, psi sub alpha inverse, if we acted upon this, what we want to do is we want to map this element of f adjoint alpha to the representative element of the factor ring f of x mod the principal ideal generated by p of x. And we can do that pretty simply by just converting this into a polynomial and adding it to that principal ideal. So we replace alpha with x and we leave f fixed, express that it's a polynomial. And then when we find psi sub beta of this coset right here, then we map whatever this would be under the evaluation homomorphism with respect to beta. When we do that, then since evaluated at p of x is going to be 0 because we assume that they're conjugates, then we get this element right here, which is exactly what we wanted. It leaves everything in f fixed, and it maps alpha onto beta. Now, the consequences of this result. One of the preeminent goals of abstract algebra is to prove the impossibility of the quintic, which is that not every polynomial of degree greater than or equal to 5 is solvable by radicals over the field of rational numbers. This is also true in general for fields of characteristic not equal to 2, but most notably over the rational numbers. We achieve this through Galois theory. Galois theory directly relates finite normal extension field, which is a subject that is developed later, to groups of automorphisms of those fields that leave intermediate fields of those extensions fixed. And despite the simplicity of this theorem that we proved here today, it is essential to Galois theory because it provides a framework for the structure of algebraic extensions, and it gives us a basic paradigm for the isomorphisms that are between these algebraic extensions. And that is absolutely essential to the interplay between that field theory and the group theory. Oh, in conclusion, conjugation isomorphism theorem relates algebraic elements. It's a ready consequence of rigorous development of theory that we've developed over a long period of time, and it is a cornerstone for even more profound and noteworthy results. There's the one source that I used. I hope you all enjoyed this presentation and continue to research this topic further.